Hey everybody, PCB Junkie back with another video. Today I have something pretty special for you guys. This right here is a project that I've been working on for quite a while, too long in fact. It's something that I spent countless hours on. At this point I don't even want to think about it. And finally we're at a point where I can demo this thing to you guys, and I'm actually pretty excited about it. So I hope that once you see this thing in action, you'll be just as excited as I am. I find this thing to be pretty awesome. So let's get into it. Let's talk about what this actually is, and if you haven't figured it out yet, maybe this will help. Yes, so it is yet another Raspberry Pi to JAMMA adapter. So I guess you're asking yourself, why make another one? I mean, there's a bunch of these already out there. What's the point of this project? Well, I guess let me begin by saying that I wasn't the last person to start this. This was actually in development for quite a while. I guess maybe even 2 years ago. This was approximately 80% finished, and it just took a lot of time. There was the development of the board, the various iterations. Then I had to work on the firmware, the drivers for this thing. I'll get into that in a bit more detail later, but it did take quite a while. And of course, at the end of the project, I had documentation and procrastination, and this it took a really long time. So while I may not be the first to the finish line, I was definitely one of the first few people to actually start a project like this. But anyway, the end result, I think, is in fact better than most of the other ones out there. And I'm not just saying it because this is my project. I do actually believe it. Let me tell you why exactly. Number one, the simplicity of the design. So what you see here is a single GPIO header. This is the only point of contact with the Raspberry Pi. Raspberry Pi plugs in here, it gets its power from here, it sends its video out through here, the sound, and also gets its control and other information through this header. There are no additional wires that need to be plugged in. The Raspberry Pi doesn't look like it's on life support. It's a nice, neat solution that looks great when everything is put together and is plugged into your harness. In addition to all this, since I was able to develop this interface from the ground up specifically for this purpose, I'm able to do things that would not be normally possible with off-the-shelf hardware when interfacing with the Raspberry Pi. To give you an example, had I used I2C or USB communication, I would be limited to the drivers provided by the hardware manufacturer, but since this was all developed by me with a custom microcontroller and a custom interface, I'm able to take full control of the drivers. Now, of course, that meant I had to develop the drivers by myself, but I'm able to prioritize the communication that is of importance to us. And in this particular case means prioritizing the inputs from the controls. So one of the major problems with emulation is input lag, and the solution that we have here is a very simple set of latches that have a serial output, which is then fed to this microcontroller, which bounces that back to the Raspberry Pi. And that communication happens at a very frequent rate. The current drivers are set for 240 updates per second. So think about that. That's 4 updates for every emulation frame, right? Assuming, of course, that you're running your emus at 60 frames a second. This is a complete overkill, but it just shows you the potential here. We're able pretty much to eliminate hardware side lag as far as the controls are concerned. Let's talk about video conversion. So the idea here was to have the Raspberry Pi generate a digital image and a digital video signal at the native resolution of the game that is being emulated. And what I mean by that is, let's say you're running a Sega Genesis emulator, which is typically 320 by 240. That video signal with the proper timing and the exact resolution would then be generated by the emulator, which means the emulator is not wasting time drawing pixels that it doesn't need to be drawing. The emulation is in fact pixel perfect with no interpolation, no scaling, and it is then sent out through the DPI interface of the GPIO header to the simple analog to digital converter. And this set of resistor arrays that you see here is where the video conversion takes place. We take the digital signal and we simply convert it to the analog format in one single step. We don't need any additional circuitry. We don't need any plugs for HDMI. We don't need any expensive scalers or converters. The image that's generated by the emulator on the Raspberry Pi gets translated directly to the video that you'll be seeing on the screen. And that eliminates a whole bunch of issues. It'll eliminate any sort of artifact that may be a result of scaling, like the shimmering that you typically see. And in fact, I would say that the image quality is pretty much indistinguishable from the actual game that should be running off of a regular PCB. For sound, we do something very similar. We take the PCM digital sound output from the Raspberry Pi header, we send it through a digital to analog decoder, which is then fed into the amplifier, and that amplified sound output goes out through the JAMMA connector right here to whatever it is attached to. Again, as with the other circuits, this is a simple and effective solution that does exactly what it's supposed to. So I guess you probably noticed so far that all of these components, all of the active ICs, active parts, are all socketed. Why is that? Why do this? Why not just use surface mount components and save a whole bunch of time and effort in assembly and cost? Well, there's a very good reason for this. I want you guys to be able to fix your own boards. I want you to be able to troubleshoot and repair the stuff you buy from me, and there's no other way really to do this if you use surface mounted parts, right? I'll give you an example. This bank right here, this is a series of latches, or actually shift registers that get the input data from all your buttons and switches and joysticks. Let's say you plug this in wrong. Let's say you flip the connector backwards, right, and you feed your 12 volts and your -5 into the section of the board. Well, you're gonna fry all of these. So these actually serve as protection for the microcontroller. I could have just as easily bought a microcontroller that's surface mounted, that has a whole bunch of pins, and hooked them up directly to the section. Wouldn't even need these pull-ups, but I didn't want to do this, because if something goes wrong, you're basically frying the whole board and making it useless. If you make a mistake like this with this, all you're gonna have to do is replace these 4 chips, most likely. I mean, you potentially could fry everything else too, but even if, right, you just simply replace whatever's broken. And you know, most of these parts are like pennies, right? I think maybe the most expensive part is this. It's like a couple of bucks, right? But these are probably like, I don't know, $2-3 for the 4. So yeah, just swap them out and you're good to go, right? And this will allow you to troubleshoot things easily, and if something goes wrong, you can just pull it out and replace and see if it fixes the problem, right? So this is the main reason I wanted to do this, because I want you guys to be able to just take care of your own stuff that you get from me. Just want to mention a couple of things about some of the other features of this adapter. Let's start with this header up here. This header is your typical Street Fighter 2 compatible kick harness header, and this is where you would plug in your buttons 4, 5, and 6 from your 6-button Street Fighter 2 type cabinet. if you don't have 6 buttons or you don't have a kick harness, you'll be able to use up to 5 buttons through the JAMMA edge connector here. This EXT header that's not currently populated, this is a future expansion for different types of controllers, like let's say trackballs or spinners that I have not yet implemented, but probably will in the future. And then finally, on the other end of the adapter, we have a sync header, and this sync header provides you with different types of video sync options. So normally in a JAMMA configuration, you only have access to a negative composite sync through the JAMMA edge connector. This header right here provides you with all the other possible video sync options. So if you have a monitor that doesn't support negative composite sync, you can hook it up to this header right here. And then, just to wrap this up, we have a couple of LEDs, and these LEDs are going to be pretty useful to us for troubleshooting and to understand what's actually happening with this board as it's booting up or while it's operating. So based on the types of flashes that we have, we can figure out exactly what's going on with this board. Now we'll talk about that in a little bit more detail when we actually get this thing up and running. All Raspberry Pis with the 40-pin header are compatible with this adapter. So this pretty much consists of anything from a Raspberry Pi 1B, which is what we have here. This is the first Raspberry Pi with the 40-pin header, to a Raspberry Pi Zero. This is a great emulation platform. It's $5, and it's actually faster than this one. I think this is like a 1.3 gigahertz, while this is only a 1.0. And it runs some of the older games, like early 80s stuff, pretty well indeed. So it's a great choice if you want something pretty inexpensive to toss into your older cabinet or what have you. And then finally here we have a Raspberry Pi 2. This is what I'm going to be demoing to you guys most of the time going forward. But of course you can plug in a 3 or a 4 as well, as long as of course it has that 40-pin header. The first Raspberry Pi, like I said, it doesn't. I think it only has like a 36-pin header, not compatible with this. Alright, so basically you just simply take this and you just shove it on there. Let's see if I can do this on camera. Yeah, that's it. And then you just push down and you made yourself a nice little emulation sandwich. So I think I pretty much covered everything that I wanted to talk about. Now I got my Raspberry 2B Plus plugged into this adapter. I got my SD card with a whole bunch of ROMs. First we're going to cover some horizontal games. We're going to talk about consoles, video modes. Then for the end of this video I'm going to switch to arcade video games. We'll talk about horizontal games, and then we'll switch to my Raspberry Pi 1, which was in my vertical cabinet. It's got a whole bunch of vertical ROMs. But you didn't come here to hear me ramble non-stop. Let's plug this thing in and get the show on the road. Alright. Okay, here we go. Okay, now that I have the PJ board and the Raspberry Pi plugged into the test rig, we're going to turn on the power and we're going to watch this thing boot up. So the first thing you probably saw was a quick flash of the status LED that indicates a reset condition. Then you saw a quick flash of the communication LED, which then slowed down. So the quick flash tells us that the PJ board is looking to communicate with the Raspberry Pi, but has an established communication. A slow blink like this means that the communication has now been established. So we're just going to wait for the drivers to load up here. Now mind you, this is a Raspberry Pi 2. It takes a little bit longer than normal. I suggest you go with something a little bit faster for emulation, at least a Pi 3. But anyway, here we go. We're going to load up the emulation station front end. And here we are. So I'm going to start this with consoles actually. We're going to bring up the Sega Genesis Mega Drive emulator and an old favorite of mine, Sonic the Hedgehog 2, just to show you guys the video quality. Alright, let's start the game. I'm going to show you some of the pixels up close. As you can see, video quality is very good. There's no interpolation. It's literally pixel perfect. So let me start the game now and show you how it controls, and we'll have a look at the lag, the input lag. Alright, so here's Sonic with Tails. Okay, now I'm just gonna basically tap the jump button and I'll show you that it's pretty much, the lag there is pretty much undetectable. Right, so that's gotta be like what, a tenth of a second or less. Definitely acceptable, at least for my standards. And then yeah, just have a look at the pixels again. Right, again, no interpolation, everything looks nice and sharp, even when in motion, even when scrolling. There's no shimmer, no scrolling artifacts, and no scaling artifacts. Okay, now if you want to quit the game, the default configuration is start and a coin button. Alright, so we'll do that now. There we go. And now we're out of the game. I want to talk to you about one thing here, which I think is pretty important. I got Contra 3 up and running, another one of my favorites. But for this part, I want to just briefly talk about the various different resolutions that you'll be running into while emulating different games, right? So here we have a Super Nintendo emulator. Super Nintendo, if you don't know, runs at a typical horizontal resolution of about 256 pixels. I believe it's maybe the number isn't exact, but 250-ish, I guess. With other emulators, we can have, let's say, up to 320, even more in some cases. And since we're drawing the pixels at pretty much the same frequency, no matter which emulator we're using, and this is the default operation of how this is all set up, there's something we can do to change that. Now, a line is always going to be a line. This line is drawn at the same frequency. This is just, we're basically just defaulting to the standard behavior of a standard resolution monitor. This is like the NTSC signal. So the lines we cannot stretch. However, we can stretch the pixels, how often the pixels are drawn, right? And we do this by changing the pixel clock. So as you can see here with the Super Nintendo emulator, we're not actually reaching all the way to the edge of the screen because we only have 256 pixels, and this is currently set up for 320 with the pixel clock of this is a 6 megahertz pixel clock. So we can slow that down. We can slow it down to 4 megahertz, and that will basically give us like 33% more pixel width, right, which will fill in the rest of the screen. So I want to show that to you guys, and I'm gonna go and actually flip the setting right now. I've got my network interface connected, so we're gonna log into the Raspberry Pi. We're gonna flip it, and then I'm gonna show you the end result. I will provide the scripts for you guys if you want to do this. If you want to modify your emulator startup scripts, you can basically change the horizontal and even the vertical resolution, even though the vertical is not really going to make that much of a difference, because again, a line is a line, but the horizontal resolution can be modified somewhat to give you various width options. Okay, so again, I provide the scripts for that and a little bit of documentation on how to do that. And if you're not happy with this, you want to stretch your screen out a little bit more and just don't want to mess around with your width setting on your monitor for every emulator, then yeah, there's going to be an option for that to make that change somewhat usable. Okay, so let me just jump to the shell there, and I'm gonna make the change in the settings, and then we'll come back in a bit. So I pulled up two of the scripts that I created for changing the various horizontal resolutions here. We have one up here for 256 pixels, and then another one for 320 horizontal pixels. And as you can see, the main difference between these two setting lines is the pixel clock. So this is 6.4 megahertz. This is the fast pixels, the narrow ones, and this is the 4.8 megahertz pixel clock, which gives us fatter pixels, right? And I've already executed this one here. You can see that the mode's been changed, and you can do this basically in the initialization script for each MU. Even for each game, if you wish, you can adjust that accordingly to you know, get the right type of width that you're looking for. Mind you, we only have a limited amount of frequencies that are available. I know these are available here, this 6.4 and the 4.8. I'm not sure if there's another one. This is something you would have to experiment with and see if you can get that working with other frequencies as well. But anyway, let me start up the MU with Contra 3 again, and we'll have a look and see what that all looks like now. So I'm expecting now to see the screen fully filled in. The pixels are a little bit fatter, as you can see. And yeah, the game should now be pretty much in full width, right? So yeah, this is pretty much how you would do this, and like I said, I provided the scripts for you guys if you want to experiment with that. If you're not happy with the width that you currently have with your emulation, you can change that in this particular manner. I'm going to show you some more console emulation. I'm going to start off with TurboGrafx 16 or PC Engine, and we're going to demo some Bonk 3. This is a great classic. It's one of the best games on the platform. As you can see, again, everything looks great, no scrolling artifacts. Pixels look nice and sharp. Big sprites. That's what the PC Engine was known for initially. Huge sprites. Yeah, it looks great, right? We of course have to do Super Mario 3 on the old NES. Again, everything looks great. Let me start the game. One-handed. Here we go. Oh. See how far I can get. Oh, not gonna be that far. Yeah. Oh no. Ah, well. Anyway, as you can see, looks pretty good, right? No issues there for sure. Okay, let's move on to the next thing. So of course, this video would not be complete without some arcade emulation. For this, we're gonna bring out an old favorite of mine, Street Fighter 2. I was really good at this game back in the day, and used to own people at the arcade. Used to play for hours on end on 1/4. Owned noobs left and right. Yeah, well, those days are done. We're supposed to be adults now, but anyway, we're still playing video games apparently. So yeah, this is a great game to showcase some of the graphic capability of emulation on the Pi right here. I'm gonna start this game. I'm not gonna be able to play it very well with one hand, but let's just give it a shot anyway. See if I can do a sonic boom. Yeah, doesn't this thing look pretty amazing? I mean, could you really tell that it's... Nah. Damn it, it's not even a... Come on, sonic boom. One! Oh, no. That's gonna be hard. Yeah, I can't do it. Sorry, guys. Ah, jeez. Oh, here we go. That's right. That's gonna be the only one I can probably do. Okay, let's do another. Oh, yeah. Okay, anyway. That's it. So, again, it looks great. Can you tell that it's not a real PCB? I don't think you could. I gotta show you this here. So now we're gonna put the Raspberry Pi into vertical mode, or tate mode as some people call it. And this is done by changing that last line that you see there, display rotate equals 1. If you don't have this, you can simply add it. And this goes into your config.txt file, which is in your boot directory. This is the startup configuration file. Anyway, so now that we have this set, I actually will now switch over to my new board that I put in there. This is the Pi B Plus that I had in my other cabinet. So we're actually going to demo this one now because this one is already pre-configured with some of the ROMs for the vertical mode. Alright, so let's start this up. Alright, here we go. It's booting up. I kind of missed the drivers loading up, but that's okay. Just want to show you guys the boot up procedure or sequence. So yeah, everything looks pretty good too, right? In vertical mode, it actually is pretty decent. Even the menus look quite alright. We'll just give it a second to start up, and then we'll launch some games and show you that. So yeah, this one is a bit slower than the Pi 2. It's gonna take its sweet time.
A few moments later.
So yeah, I wouldn't recommend using a Pi 1. I still have it just because I need to make sure this is all compatible, right? Backwards compatible, just in case people need it. But yeah, just go with something a little bit faster, like a 2 or a 3. Pretty much the same price anyway. Alright, so yeah, so this is what this looks like in vertical mode. I'm gonna tilt the camera this way so you can see it. Yeah, it's looks normal. Like if you put this in a vertical cabinet, it's pretty awesome. No issues there. Alright, so I think for one of the games that we should demo, we're gonna launch something that scrolls in the horizontal direction. Well, the horizontal direction at the moment, which is vertical, I guess, in real life. So let's launch Bump and Jump. It's one of my faves again. Pretty cool game. Played the hell out of it when I was a kid. Just give it a second to start up, and you'll be able to see with Pi 1 Plus, the emulation for some of these older games is pretty much flawless. And again, you know, have a look at the pixel quality. Everything nice and sharp. There's not going to be any scrolling artifacts. I probably should center the screen somewhat. Let me just do that here. Vertical position. Just shift it up a little bit. Where is it? There we go. Okay. So let's get a game started. Alright, so have a look at the scrolling. Oops, I already died. Well, that's nice. So, yep. Have a look at that. Let's accelerate. Alright. Right? So, as you can see, I know this is pretty fast. But yeah, there's no shimmering as the pixels are scrolling, right? Yeah, so this looks pretty good. Alright, this is about it for this game. We're gonna switch out to something that scrolls the other way. I'll show you that as well. So now for a game that scrolls in the other direction, let's pick Super Cobra. Again, one of my favorites. This is a really great game. I still play it every so often. Alright, so scrolling looks great. Again, pixels nice and sharp, no interpolation, everything exactly the way it's supposed to be. Okay, I just want to show you guys the shutdown procedure. So we're going to flick off the power for like a quarter second. I'm going to restore it and watch the shutdown in action. It's actually pretty quick. I'll explain what happens with the LEDs as well. Okay, so power off. Now you can see that the Raspberry Pi is going through the shutdown procedure, and you saw the light flashing. That indicated the shutdown condition has been detected, and the quick flashing now indicates that the Raspberry Pi is not communicating with the PJ board. Right, so we'll turn off the power, and basically now the power has to be depleted fully for the board to come up again. Alright, so this is going to be it for this video. I hope that you enjoyed watching it as much as I enjoyed working on this project. And yes, well, this project was quite time consuming, and it take quite a bit of effort to get it to this point that you see here. I am in fact very, very pleased with the end result. So if you're interested in getting one of these adapters from me, or just simply want to find out more information on the project, I'm going to link to the website from the video description, so please check that out. And if you have any questions, just leave them in the comment section and I'll try to get back to you that way. Also want to thank those that have helped me beta test this adapter over the last couple months, and also want to say thank you to those that have supported me while I was working on projects like this and others in the last couple years. So this is it. Once again, thanks everybody for watching. If you like what I'm doing here on YouTube, you know what to do. And I'll see you all on the next video. Bye everybody.